All right, guys. So we are back in Unit 11. Yesterday you worked with solutions determining the amount of salt that was dissolved in a 4.80 molar sodium chloride solution. And you may or may not have worked at all on the concentration problem worksheet, which is absolutely fine. You'll have the opportunity to work on it today after we're done with our discussion. So far in Unit 11, we've defined solutions and we've described them using vocabulary. We've listed factors that affect the rate of dissolving. We've calculated concentration using mass percent and molarity. And now we're going to talk about molarity, like what exactly does that mean and how do I work with solutions. So I have here a beaker of water. It's 100 milliliters of water, and to the beaker of water we're going to add some food coloring. Okay, we're going to stir this up. Okay, all right, here we go. So let's see if we can't flip this around. We have our beaker of water. Okay. In this beaker of water, I could say I have a number of moles of food coloring in 100 milliliters. And I could calculate the molarity of this. I could say, what I know is, this is going to be backwards for you guys. All right, so in this, I know that I have a certain amount. Yeah, it's upside down, sorry. The amount of moles in this beaker. Now, if I add more water, so I add water to my beaker. So now let's increase from 100 to 150. Oh, well, initially I had 100 milliliters. Epic fail. All right, we're just going to write it my way. I had 100 milliliters of water and I had X moles of food coloring. Right, now I've changed my system and now it has still the same moles of food coloring, but now it has 150 milliliters of water. And I notice that the color is changing oh so slightly. So here I can add now to 200 milliliters of water. Now I've got a new system and I have still the same moles of food coloring, but now it's in 200 milliliters of water. And every time I change the volume of water, I change the molarity. So if I look at my molarity equation, well, we'll come back here. And we'll do one of these. There we go. If I change my molarity equation, if I look at my molarity equation, this is moles of solute divided by volume of solution. Okay, so my moles of solute was the same each time. It never changed, but my volume of my solution did. And because my volume of solution changed from 100 milliliters to 150 milliliters to 200 milliliters, my molarity changed. And I did something that we call just a dilution. So a dilution, I diluted it. A dilution is when I change the volume of my solution, and by changing the volume of my solution, I change the concentration. And I can do that because the moles stayed the same. And if the moles stayed the same, then I can make some statements about my system. I can say that the moles, all right, let's flip this around. This is just getting silly. Here we go. What can I say about my system? I can say in a dilution, moles are constant. The amount of food coloring I had in this beaker in the beginning is the same as the amount of food coloring I have in the beaker now. And I could put it into a swimming pool and the number of food coloring particles is still the same. Now the concentration of food coloring particles, that will be different. So in a dilution, the moles stay constant. So I say the moles of my concentrated system are going to be equal to the moles of my diluted system. So if we look at the equation for molarity, if we solve this for moles, my equation becomes, I multiply times volume, right? Multiply times volume. My equation for molarity is volume, or excuse me, my equation for moles is volume times molarity. All right, so I can have molarity of my concentrated times my volume of my concentrated, that gives me moles. And if I have my molarity of my dilute solution and my volume of my dilute solution, goodness, that's a V, is also going to give me moles. This is moles of concentrated equals moles of diluted, which means the molarity of concentrated times the volume of my concentrated will be equal to the molarity of my diluted solution times my volume of my diluted solution. This is important because we rarely purchase chemistry chemicals in a diluted form. We almost always purchase them in a concentrated form, and then we dilute them to the molarity that we want and the volume that we want. And so we manipulate this equation a lot. Why does this equation work? Because the moles were constant. The amount of food coloring in this container did not change. And so because the moles before, or the moles concentrated, are equal to the moles diluted, I can solve the equation of molarity for moles, and I get this MC, molarity concentrated times volume concentrated, equals molarity diluted times volume diluted. All right, let's look at some problems where we see this in action. So I'm going to flip in my packet to my dilution of solutions worksheet. So front page, and I'm flipping, flip, until I get to the dilution of solutions. So it is Tuesday. All right, here we go. Let's look at some problems here. Dilution of solutions. If you dilute 450 milliliters of a 6 molar concentration, okay, so this is one set, see it's stuck together. Those are a set. And I'm diluting it to a volume of 1,000 milliliters. What will the resulting concentration be? Okay, this is my concentrated, my molarity concentrated, my volume concentrated, and this is my volume diluted, and they want me to tell them what the molarity diluted will be. So I'm going to make my variable list, MC, VC, and because I don't have a lot of space, I'm going to just jump over MD, VD. All right, let's read our problem. I have molarity concentrate, that's 6 molar, 6.0 molar. I have my volume concentrated, that's 450.0 milliliters. I have my, I don't have my molarity diluted, that's what I'm looking for, question mark. I have my volume diluted, it's 1,000 milliliters. And there's a decimal point. All right. I write my equation in letter form. I get MCVC equals MDVD. This came from my solutions box. Solution box, it's down here. MCVC, MDVD. All right. All right, we look at this. This is a proportion. There are no constants. There are no ideal gas equations, which means I can use any volume I have been given as long as they are the same. All right, so I'm not doing any converting. I can use milliliter and milliliter. Solve your equation for variable that you're looking for. I am looking for molarity dilute. I'm looking for molarity dilute, so I'm solving for MD. So I divide by VD. That cancels out my units. And I'm going to say molarity dilute equals MCVC divided by VD, where MC is 6 molar, VC 450.0 milliliters divided by 1,000 milliliters. Milliliters cancels, and I just plug it into my calculator. So 6.0 times 450 equals divided by 1,000. All right, and I check 4 significant figures, 2. 4 significant figures, by golly, 2. I need 2. So the label equals 2.7 label molar. So what happened? I increased my volume from 450 to 1,000, and my molarity, or my concentration, decreased. decreased. Logical. Yay. Okay. Continue and do numbers 2 through 5. But let's also revisit. So before, this is your homework. Okay, homework. This is your homework, 2 through 5. All right. Let's revisit some equations, some reaction types. So we learned about reactions earlier in the year, and there were different types of reactions. There are 5 different types of reactions that we have learned about, and we are interested in reactions that happen in solution. So the other day we talked about reactions that happen in solution are double displacement reactions. So the common solution-solution, double displacement reactions. And there's a special type of double displacement reactions called acid-base reactions. Acid and base reactions. Now, we are working with the definition. It's called the Arrhenius definition, of acids and bases. And this is the narrowest, the most simple definition of acids and bases. Under the Arrhenius definition of acids and bases, an acid is a substance that, when in water, donates hydrogen ions to solution. And it also tastes sour and, yeah, has a sour taste. But we're never going to taste acids in class. But there you go. Then bases, the Arrhenius definition of a base is that it donates hydroxides, OH minus ions to solution. These would have bitter flavors, and they also feel slippery. If you get a solution, a basic solution on your hands, it'll feel slippery. It's what's in soaps. So, but it can be just as damaging to your hands as an acid would be. So acids are substances that donate hydrogen ions. Bases are substances that donate hydroxide ions. On the back of your periodic table, there's a list of some common acids that we work with. Okay. All right. If we look at a reaction between an acid and a base, so if I have hydrochloric acid plus sodium hydroxide in solution, they break up into their ions, H plus, Cl minus, Na plus, OH minus, and they break up. That's what aqueous means. These are not they're no longer stuck together, but they're ions in solution, and they rearrange, forming new potential products. So my potential product would be sodium chloride, maybe, and HOH. Well, HOH, I know, is water, and that's a liquid. So the reason this reaction happens is because water is a product driving its reaction. Now, if this also forms a solid, this too drives the reaction forward to form. So I go to my periodic table, I find sodium. Down here, I find chlorine, and wouldn't you know it, chlorine, that sodium chloride, that most of the salts of chlorine are aqueous, and we know sodium chloride is as well. All right. So if I do this reaction, hydrochloric acid and sodium hydroxide, I do not get a solid. I do form water, which is what's driving the reaction forward. So what I also notice is that for every one formula unit or one molecule of hydrochloric acid, when hydrochloric acid dissociates or forms ions, for every one molecule of HCl, I get 1 hydrogen. So if I have 1 mole of HCl, I get 1 mole of H+. And because it's a strong acid, I am assuming all of my HCl in solution is in fact hydrogen ions and chlorine ions. This is for strong acids. If I look at my NaOH solution, I see that for every 1 formula unit of NaOH, I get 1 sodium, and 1 hydroxide. 1 hydroxide, and both of these are also in solution. Now, What am I really interested in? I'm really interested in the thing forming the reaction, which is the water. So I'm really interested in what's going on with the hydrogens and the hydroxides. And I see something here. I see that for every one mole of HCl, I get 1 mole of hydrogen and 1 mole of chlorine, but chlorine doesn't form, so we just ignore it. It's called a spectator ion. And for every 1 mole of sodium hydroxide, I get 1 mole of sodium ions, and I get 1 mole of hydroxide ions. 1 mole and 1 mole. So this appears to be important. Look, 1 mole, 1 mole. This is my strong base. Strong it just refers to the fact that if it's in solution, it is all dissociated into ions. That's what strong means. None of this is left. All of it is over here as ions. Well, I describe this as a solution, which means that I measure how much I have, not in moles, but in concentration. I will describe how much I have using molarity, and I'll describe how much I have of this also in a molarity. And if I know that the molarity of my hydrochloric acid is a direct relationship to hydrogen, and the molarity of my sodium hydroxide is a direct relationship to hydroxide, I can also use that same relationship. We said the moles, as long as the moles are equal. So here I see that the moles of my acid, for every 1 mole of hydrogen, it takes 1 mole of hydroxide to make 1 mole of water. My moles of acid equal my moles of my base. If I have 2 moles of hydrogen, it takes 2 moles of hydroxide to make 2 moles of water. So there's the same relationship. The moles of acid equal the moles of base, and this is called an acid-base neutralization reaction. It's called a neutralization reaction because the product of this reaction is water, and water's neutral. So if the moles of acid and the moles of base are equal, and I measure acid and base in molarity, I can use my molarity equation to calculate how much will I need. I don't have to have equal molarities, I just need to know how many moles I have. So my molarity equation, molarity is moles divided by volume. If I solve this for moles, volume, I get moles equals molarity times volume. Molarity times volume, right? We're just abbreviating it. And if moles of acid equals moles of base, then I can do something funky to this equation. I can say the molarity of my acid times the volume of the acid that I have will be equal to the molarity of the base times the volume of the base needed. So if I'm doing a reaction between an acid and a base, all I need to know is what's the molarity of the acid and how much of it do I have. And if I know what the molarity of the base is, I can calculate how much base it will take to neutralize it. Or if I know the volume of the base I used, I can calculate what the molarity of the base was. So this is the acid-base neutralization equation. And yes, it looks exactly the same as the concentration diluted equation. And they have the same structure because they're built on the same underlying concept, that as long as moles stay constant, it doesn't matter what I'm using, if I'm going from a concentrated system to a diluted system, or if I'm neutralizing acids and bases, as long as it's 1-to-1 or a direct relationship, I can use this relationship here. So acid-base reactions are just a fancy type of a double displacement reaction. It's water that's driving it. We're looking specifically at Arrhenius acids and bases, strong acids, strong bases. And if I'm working with a strong acid, strong base, I can use this relationship to calculate components of my system. All right, let's try one. Back to your worksheet. No, look at that. There's titration neutralization problems on the bottom of our worksheet. Okay. Neutralizations of acids and bases. We are going to work with MAVA equals, oh, yeah, acid. MbVb. This equation is in the solutions box. It's right here. MAVA, Okay. Again, it doesn't matter what the volume of acid or base is that you have as long as it's the same on both sides. So let's look at the problem. How many milliliters, well, that's something I'm searching for, how many milliliters of a 0.35 molar nitric acid, okay, of, these guys get stuck together, will be needed to neutralize 50 milliliters of a 0.200 molar potassium hydroxide solution. All right. These two go together. They go together. These two go together. The word of is the glue. They go together. All right. Molarity of acid, volume of acid, molarity of base, volume of base. Okay. How many milliliters of nitric acid? Right, that's a volume of acid. Question mark. The concentration is 0.35 molar. 0.35 molar are needed to neutralize 50 milliliters. Oh, that's a volume. Of 0.200 molar KOH. That's a molarity. Okay, 0.200 molar. All right. Molarity and molarity, as long as those are the same, we're golden. Milliliters, fantastic. The answer's in milliliters, not a problem. Write your equation in letter form. MAVA equals MBVB. Solve for your unknown. My unknown is VA. Here's VA, currently being multiplied. I do the opposite of multiplying, which is dividing, to move it to the other side. I have my volume of my acid. I'll zoom in here a little bit. Volume of acid equals molarity of base times volume of base divided by molarity of acid. So let's plug our numbers in. 0.200 molar times the volume of base, 50.0 milliliters, divided by the molarity of the acid, 0.35 molar. Yes, label, no naked numbers. Molarity cancels, leaving me with milliliters remaining. Okay, grab your calculator. 0.200 times 50.0 equals, divided by 0.35 equals, oh, let's look. I had two significant figures, 3 and 3. I will round to the smaller number, which is 2. So keep the 2, keep the 8. The 5 rounds the 8 up to a 9. And my answer is 29 milliliters of nitric acid. Nitric acid. Okay, does this make sense? I'm saying it's going to take less milliliters of acid than base. Okay, it's not a crazy amount less, it's still tens of milliliters. And then I'm like, oh, look, this is a stronger acid. It has a higher concentration, so that makes sense. If it has a higher concentration, it should take less volume of a base that has a higher volume and a lower concentration. All right, guys. 2, 3, 4. That is it. 2, 3, 4 is your homework. And this also means that some of those problems that you may have saw on the concentration review worksheet, this concentration problem review, some of the problems that were on there that might have been like, what, did we learn this? Well, the answer is no, you didn't, but now you have, and you'll be able to work through them as well. So complete this if you have not already. I will post the answer key when I come back. I really want you guys to work through this on your own and give it a shot. And by on your own, I mean not looking at my homework. All right, guys. Have a fantastic day. Best of luck. Work through your homework and then complete the rest of the lesson.